Welcome to the Smart Grid Cybersecurity demonstration. In today's demonstration, we will see how a smart grid works, why securing the smart grid is important, and how we can secure the smart grid. In today's presentation, we will mainly focus on a critical component of the smart grid called the Phasor Measurement Units, or PMU. A PMU is a field sensing device that's connected to medium or low voltage transformers of the grid, and it measures voltage and current phasor information and frequency of the electric bus at a particular location of the grid. And it sends or communicates this measurement information about the electric bus to the control center. And at the control center, we have a node called the phasor data concentrator, or the PDC, that receives the stream of data from different PMUs in different locations of the grid. It aggregates this piece of information from those different PMUs and puts it into a single stream and pass it to another application called the state estimator. And this state estimator takes this stream of data from the PMUs as an input and outputs an estimated state of the overall smart grid network. And this estimated state gives us information about the current stability conditions of the grid, and it also gives us hints about possible instabilities and perturbations. And these possible instabilities can also trigger the control center to issue control actions to correct those instabilities and bring back the smart grid to a stable state. So in short, we can say that the PMU is considered as the eyes and ears of the smart grid, whereas the control center can be considered as the brain of the smart grid that processes the information that's received from the different eyes and ears and gives meaning to what the current condition of the smart grid is. So now let's look at a typical component of the smart grid network called the active distribution network, and let's look at the different components of this active distribution network. We have a bulk generation power plant and a substation with high voltage to medium voltage transformer, and at this location we may also have energy storage banks, and at the distribution premises we may have windmill farm and photovoltaic voltage in the city of consumers, electric vehicles, and of course the control center, which is tasked with supervising the state of the smart grid and giving control actions to make it stable and operate in a stable condition. And of course we also have the PMUs deployed at the different critical locations of the grid to send high frequency information about the current state of the grid to be processed by the control center. So during a smooth operation, energy is generated from those different generation locations, and information about the grid is communicated from the PMUs to the control center. And now let's look at a scenario when there is a bulk of generation and less consumption at the consumer's premises, and this bulk of generation could cause perturbation at the smart grid. And conventional smart grid networks may know about the existence of this perturbation, but they may not know what caused this perturbation. But thanks to our high precision, high frequency measurement devices called PMUs, our control center gets more defined and refined information about the grid, and this information helps the control center to know why the perturbation happens, and in fact it knows that the perturbation happened because of an upsurge of power generation from the different locations. So after processing this information, the control center may decide to send control action to turn off the windmill to lower the energy generation in the grid and bring back the stability. So by doing that, if we turn off or shut down the windmill generation, then stability will come back and the grid will be back to its normal operation. And now let's look at the effect of a cybersecurity attack on the smart grid. Let's assume a terrorist group or an enemy state wants to destabilize our smart grid network. And this enemy state or terrorist group, for example, may hire a group of cyber criminals to compromise and replace the PMUs that are deployed at different remote locations with no manned security. So it could be easier for these criminals to replace them with rogue devices that send wrong information about the grid instead of the correct measurement of the grid state. So this wrong information will give false information about the state of the grid to the state estimator, and the state estimator will output wrong state about the grid. And this wrong state could cause the controller to send wrong control signals, or it may also cause it not to send any control signals when actually it needs. For example, to go back to the previous example, if there is a high generation of energy, or if there is an upsurge of generation of energy in this location and there is less consumption, the control center was supposed to send control actions to turn off the windmill farm generation or other generation locations. And in our case, instead of turning off the windmill, it may just cause the turn off the photovoltaic generation, and this photovoltaic generation, turning off this photovoltaic generation may not have any significant effect. So, which means the perturbation in the grid will continue, and in fact it may even cause a total blackout in the smart grid. So what's the solution for this kind of attacks? Of course, the obvious solution is to deploy appropriate cybersecurity solution. In our demo, we will use a cryptographic solution to protect against eavesdropping and bad data injection from those field devices to the control center. So in this case, since the communication between the PMUs and the control center use UDP protocol, we will use a DTLS protocol for encrypting and for message authentication for all communications between the PMU and the control center. So what's a DTLS protocol? A DTLS protocol is actually a UDP version of the TLS protocol, so it gives us similar security guarantees as a TLS protocol gives to TCP flows. In other words, it gives us data origin authentication or message authentication and integrity check using MAC protocols. It also gives us confidentiality by using encryption using symmetric key algorithms. Plus, it also uses digital certificates during the initial phase. So DTLS has an initial phase called the handshake phase, by which two communicating partners authenticate each other or verify their identities using digital certificates. And during this initial handshake phase, they mutually authenticate their identity, and they also agree on different algorithms that they will use to communicate data, and they also establish the cryptographic keys that will be used to encrypt and to authenticate the message during the later on communication. And the digital certificates that are used for the handshake phase are actually issued by a third party called the Trusted Certificate Authority, which is trusted by both the PMUs and the PDC. So let's look at how a digital certificate is issued. Let's say we have a device called device A, which has a key pair with A public key and S private key, and we have a certificate authority which also has a key pair called the CS public key and the CS private key. So device A wants to get a certificate from the certificate authority, so it sends a certificate request by saying, this is my identity, I am device A, and here is my public key. And it says, please provide me with a certificate that is signed by you. So the certificate authority takes this request and signs the information it contains. This is S public key, and I testify that this is S public key, and it signs it using its private key to help others verify that this is actually bound to, this public key is bound to the S identity. So now that A has its own certificate, let's look at how the communication, a secure communication and authenticated communication can happen between device A and device B. So if device A wants to send data, sign data to device B, it can take the plain text, signs it using its private key, and sends this signature plus the plain text to device B. and device B wants to verify this signature and to verify that this signature was signed by device A. Since device B has the knows and trusts the certificate authority and knows its public key, it takes the certificate, device A certificate, and verifies the authenticity of this certificate by using the certificate authority's public key, and again picks the public key part of the device A certificate and verifies the signature that's received with the plain text using the public key part of the certificate. So now let's look at how the system setup looks for our demonstration. We will have a control center that receives a stream of phaser data from 4 different PMUs, and the control center will aggregate this and gives it information to the state estimator. And since we will use a DTLS security solution, we will also have a trusted certificate authority that issues certificates to the 4 PMUs as well as to the PDC. So these PMUs and the PDC will use their digital certificates for mutual authentication during the handshake phase of the DTLS, and then they will use the session keys that are set up during the handshake for securing the communication of the phaser, synchro phaser data between the PMUs and the PDC. And to demonstrate the attack, we will replace the 4th PMU by a rogue device which doesn't have any valid certificate which was issued by a trusted certificate authority. So we will see that the PMU, the 5th PMU, which is trying to send synchro phaser data to the PDC, will not succeed because the initial handshake, which required a trusted certificate from a trusted certificate authority, will fail. So in this case, in a secure communication of the smart grid, what we'll see is the PMUs that are compromised will still try to send data to the PDC, and the PMUs that are not compromised will successfully pass through the handshake process and send their data in a secure way to the control center, whereas the PMUs that are compromised and replaced by rogue devices will still send data, but since the handshake fails, this data will not reach or will not be processed by the PDC. So that means the control center will still have only a subset of the information, and part of the other information will be ignored. So we'll still have loss of information, but it's better to have loss of data than to get wrong data from wrong devices, which will mislead us about the current state of the grid. Let's now look at the video of the lab demonstration. So now I will describe the system setup that we use to demonstrate our security solution. So here we have 5 PMUs, where 4 of the PMUs have valid certificate signed by a trusted authority. And the 5th one has 2 certificates, one signed again by the trusted certificate authority, and the other one self-signed, which is a not trusted certificate. And here also we have the PDC. Again, it has a valid certificate signed by the trusted authority, which can be used to authenticate itself to the PMUs. And we have the application where we have the graphical user interface, which shows the decapsulated data that's received from the PMUs and the state estimator output. And here we have the console where I will be starting the application that receives a stream of data from the PMUs. And I used this PC to remotely connect to the PMUs using SSH and start the application that streams data from the PMU. And I have 5 terminals that I use to log into the PMUs. So to start with, what we'll do is we will start the application from the 4 PMUs that have valid certificate. And on the PDC side, we start the application that receives the streams on 4 different ports for the 4 PMUs. And to demonstrate the attack, we will also use the 5th PMU as a rogue device to show that an attacker could use a rogue device to introduce bogus synchro phaser data to spoof a PMU with valid certificate. And with our security solution, we will see that it actually doesn't succeed to successfully stream synchro phaser data to the PDC. because there is this initial handshake phase where the PMUs and the PDCs mutually authenticate each other, and this mutual authentication fails if the device doesn't have valid certificate. So to start with, let's start the processes from the 4 PMUs that stream data to the PDC. So I'm starting 4 applications to stream to the PDC, and on the server, on the PDC side, I'm streaming the listening application to the synchro phasor data. So we see that the handshake phase for the 3rd PMU, 4th PMU, 1st PMU, and the 2nd PMU, all 4 PMUs have successfully authenticated to the PDC. Likewise, since the authentication is mutual, the PDC also authenticates to the PMUs. And this means the PMUs can now start streaming application data. And here we have LEDs that display if the PDC has received config packets from the PMUs. So we already have received the config message from 2 PMUs, and we'll wait until we receive config message from 4 PMUs. And so once the PDC receives this config message, it will display the actual application data here, and that verifies that the PDC has successfully decrypted and authenticated the message that's coming from the 4 PMUs. So let's wait a little bit until we receive the 4th config message from the 2nd PMU, and we'll see that the data will be displayed here. And in this interface, we also have the application, the total latency required. So here we receive all the traffic coming from 4 of them. And here we display the total latency used to compute the message, starting from the streaming from the PMUs up to the output of the state estimator. It takes up to about 59 to 60 milliseconds. So this is when everything is all right and when all PMUs that are trusted are streaming to the PDC. And now we will emulate an attacker by which we replace the 4th PMU by the 5th PMU, which has a rogue certificate. And for that, let's stop the streaming application from the 4th PMU, emulating that somebody is replacing it with a rogue device. So when we stop it, we see from the PDC side that the application actually stops receiving data from the 4th PMU. And on the 5th terminal, I will start the rogue application from the 5th PMU, which tries to authenticate itself to the PDC and start streaming. So when I do that, I see that on the PDC side, the authentication fails because the PDC doesn't trust the certificate that's presented by the 5th PMU. And again, the application doesn't receive any traffic coming from this 5th PMU because for the PDC to receive data, it has to first authenticate the device, and the authentication has failed. And so now, since the 5th PMU has 2 applications, one with the trusted certificate and the other one with the rogue certificate, now I will stop the rogue certificate because we didn't receive anything. And I will start the 2nd application, which is the valid certificate. So if I do that, we see that on the PDC side, the PDC now successfully authenticates the certificate, and it actually also decrypts and accepts the stream of data coming from that 5th PMU. So from here, what we can see is that the security solution that we implement here actually ignores data or doesn't authenticate devices that are not trusted by our certificate authority, and it successfully accepts this data coming from trusted devices. Plus, we also show that the overhead that's introduced because of the security solution is negligible. We see that the difference between the latencies when there is no security solution deployed and when there is significantly minimized. In conclusion, we saw that cyber attacks can have catastrophic consequences on smart grid stability. We also saw the need for operators to implement proper cybersecurity solutions. And in our demonstration, we showed a DTLS security protocol that provides fast encryption and message authentication with negligible performance overhead on the smart grid application. And our DTLS security solution may cause some data losses if there are cyber attacks. Of course, it will ignore those data coming from the compromised devices, but it's better to have data losses than to have wrong data from those compromised devices. And in fact, data loss can be recovered by using redundancy solutions, other redundancy solutions to recover those lost data. So that was it for today's demonstration, and thank you for your attendance.